While Lapis now harbors many different swimming clades, only one is truly comparable to our fishes. While the sea nuts still dominate the pelagic world, they are decidedly not Piscean. The vagile multigelatiforms, on the other hand, are so alien-looking that they can hardly take the helm of fish, even without considering their minimal ecological presence. Conversely, the finworms are superficially Piscean but are too negatively buoyant to fill roles one would expect of an alien planet's answer for fish. The very structure of Lapis's biosphere seems to stand in defiance of the very concept of fish. Planktonic niches typically held by the larvae of fish and crustaceans on Earth are instead filled by single-celled organisms and the microscopic offshoots of a bygone era. Instead, Lapis's fish have arisen from the unlikeliest of origins. Lapis's fish are not bilaterally symmetrical, nor are they radial. Lapis's fish sport glide reflection. Pectantaculins are already disassociated with most other life forms. They, alongside Crispellis, constitute the last linguisamirians and the last of the dilatarians to maintain both motility and glide reflection. Humble, slug-like creatures cowering between slabs of rock and calcareomorphs may seem ill-suited for a Piscian lifestyle, but the adaptations they do have allowed them to proliferate through Lapis's reefs. Pectantaculins have a very simple through gut and an unspecialized mouth and throat. Unable to eat anything else, they subside by preying on tiny, soft-bodied greenworms and by sifting the sand with their tentacles for detritus, exovorams, and exobacteria. The sands of reefs are particularly bounteous, given their exceptionally high population density and ecological productivity. Unfortunately, accessing their feeding grounds more often than not requires leaving the safety of their rocky crags. Thick skin with chainmail-like calcifications, a barrier of unsavory slime, and mildly toxic blood deters many predators after a good few attempts. But the longer finworms have to adapt to these defenses, the less effective they will become. The pectantaculins have come to rely on an interesting quirk of biology we have yet to discuss: horizontal gene transfer. In essence, horizontal gene transfer is the migration of genetic material between unrelated organisms, even those of different species. On both Earth and Lapis, these kinds of unexpected trades are most often made by bacteria. The thievery and spread of traits such as chemical resistance and the ability to metabolize different substrates has been perfected by Lapis's scum for billions of years. Very complex organisms are less inclined to this strategy, since they risk altering the teetering balance of their own functionality. Nonetheless, this strategy is one of the leading causes behind the persistence of the linguisamirians into the Worm Age and beyond. Their toxic blood, and their own immunity to it, was hijacked from the microbial world, with each species amassing their own unique concoction. At least one pectantaculin opened Pandora's box. Once locked away in a prison of rot within the sand, the genes for producing chlorocruerin were unburied and unleashed. This trait was rapidly platonically spread through the population, seeding the stem line of zipper eyes. This is a zipper eye, Lapis's echo of fish. While it may seem distant from its recent ancestors, it is strikingly similar. A comb of wispy tentacles brushed the seafloor from a hammer-shaped projection at the front, driven along by a muscular, mucosally driven foot, as per usual. While the hammerhead has bifurcated into a section of devoted feeding tentacles at the middle and multi-purpose walking and sensory ones on the outsides, it is fundamentally the same structure. Similarly, the foot has split into two as well, with one half extending above the walking foot to form a swimming tail. Many swimming animals we know from Earth, as well as the finworms hailing from Lapis, power their movements utilizing symmetrical muscle bands. With a cascading signal from the brain, a wave in the activation of these muscles undulates the body. Organizing the muscle bands into a glide reflection does not alter this outcome. Partly due to their U-shaped cross-section, and also in order to prevent disturbing the substrate, zipper eyes swim with a lateral or side-to-side undulation pattern. When searching for food in the sand, they walk on the seafloor with a combination of slithers and hops of the foot and pitter-pattering of their little tentacles. If disturbed, these little fish quickly dart away, seeking refuge among the calcareomorphs and lanelomorphs. By using the sticky foot, they can cling to and crawl over any surface. Suddenly escaping behind an obstacle and sticking to something just out of view baffles most predators. When resting, they sometimes go as far as bullying small finworms off of their perches, not for any higher purpose, but simply because they are better at clinging and they compete for the same resting spaces. Many of the basal zipper eyes live in and around reefs, but our example species actually prefers the liminal deserts, particularly among the deepwater barreriforms and stolensipitiforms. Roosting on these towering lanelomorphs keeps them far away from the hungry octanguipeds and finworms down below. At their small size, even spinofascia and sand nuts pose a threat, let alone wormhole assassins. Luckily for the zipper eyes, their striped pattern simultaneously disrupts their outlines and camouflages them into the tall lanelomorphs. Even the lapisaucers pay them little mind. Zipper eyes have a few more adaptations that shouldn't go undiscussed. First, their namesake zipper of eyes.